Today's video is on section 2.2, basic differentiation rules. Your homework from 2.2 is 1 through 61 odd. So this is going to be a lot of notes. It's not that it's that difficult, it's just a lot of notes because I need to give you all the rules. So what I'm going to do is, this is what we've done already in section 2.1, finding the derivative by the limit definition. So here is some given function, and I want you to go and find the first derivative. So here is how you would go and find that first derivative. So the first derivative, or in other words, the slope of the tangent line to the graph of f, is the limit, and it was the function where you input x plus delta x minus the original function all over delta x as delta x goes to 0. So where I saw an x, just like you did, I put in x plus delta x plus delta x, minus, and then just the original function. And then we had all that algebra to do. Right. So I did this squared, got all that. I distributed the negative, right, which is what you were doing. And then I went and I distributed the 3 to each of these 3 terms. Now I have a bunch of terms, and I'm going to see what I can cancel out. For example, the negative 1 and the positive 1, the negative 4x and the positive 4x. And so what I had left over were the 3 terms with delta x in them. This one, this one, and this one. Which again, my whole goal is I'm trying to take the limit, and I can't. Because if I put 0 in here, it's undefined. So I need to be able to factor out the delta x out of the denominator, and I'm going to be able to do that. I factor out a delta x out of the 3 terms in the numerator. I'm able to cancel that out, divide that out top and bottom. I can go ahead and then substitute in 0 for delta x, and I get 6x plus 4. This is what we did in section 2.1. This is the only way you know how to find a derivative until now. Here's our goal for today. Today our goal is to find a derivative by using differentiation rules. So for example, here's that same function. Once I give you that function, after I go through these notes, you'll be able to find the derivative this quickly. Done. I used the rules in order to find the derivative. I did not have to go through all of this tedious math. Look at, I got the same thing. I got the same thing. But you don't know what I used. So let me show you what I used. Before I begin, let me go over the different ways that you might see the first derivative being written, which again is the slope of a tangent line to a function. So you've seen it like this. If I gave you f of x, if I give you y, I could put y prime, and that means first derivative. This means the derivative of y with respect to x. We will use this quite a bit. Same thing. The derivative of y, so my y function, y equals whatever it is, and the variable is x. Well, yes. And you know y could also be f of x. It's the same thing, right? Kind of like here. So now I'm saying I'm taking the derivative of f of x with respect to x. All of those means the first derivative, all of those. Now I can begin. Here is the first rule. It's called the constant rule. Remember, constant is just a number. So if I have something like y equals 2 or y equals 5, which is a horizontal line, these are all horizontal lines, then what? Then when I take the derivative of y with respect to x, which in other words I'm taking the derivative of that constant with respect to x, is equal to 0. But that makes sense. If I have some function, there it is, y equals, let's say 2, that's my c. Well, the first derivative is the slope of the tangent line anywhere on this graph. Isn't the slope everywhere on this graph 0? So that's why the first derivative is 0. Because my original function is a horizontal line, and everywhere in here the slope is 0. And then I have two examples for you. If I have y equals 2 and I tell you to find the first derivative is equal to 0 from this constant rule. If I give you f of x equals 4, which is still y equals 4, horizontal line, then the first derivative is equal to 0. I could write this like this. I could have also written it like this. They all just mean the exact same thing. Next one, power rule. If I give you y equals x to the n, then what? Well, when I take the first derivative of this, of x to the n with respect to x, this is how I do it. I take the exponent and I bring it down, I multiply it by x, and then I take that exponent and I decrease it by 1. That's how you do that. So let's do a couple of examples, or let me show you a couple of examples. Let's say I give you y equals x to the 4th. Now I'm telling you, you must write this. If you do not write this, I do not know what you're doing over here. You must tell me this is the first derivative. You must tell me this is the original function. So up here it told me to take the exponent and bring it down in front, multiply it to the x, and then decrease my exponent by 1. So in other words, my first derivative is 4 times x to the 3rd power. What if I gave you f of x equals the cube root of x? I can use this power rule also, but first thing I must do is I must make it look like this. So I must rewrite my original function. See, that's not the first derivative. So the cube root of x is really x to the 3rd power. Now this looks like this. Now I'll be able to use the power rule and not make any mistakes. So here it comes, the first derivative. I'm going to bring down the 1/3 times x, 1/3, decrease it by 1. That's what it says. And I'm going to clean that up. That's 1/3 times x to the negative 2/3, right? But you may not leave your answer like that either. The first derivative is equal to, this is in the numerator, this is in the denominator, that is in the denominator, now it's got a positive power. Sorry, that is a power. That's not x times 2/3, that's x to the 2/3 power. Kind of wrote that large. And then this is done, all cleaned up. I want no negative exponents. I want everything in its proper place, numerator or denominator. Let's do another example, still in the power rule. What if it says y equals 1 over x squared? And I want you to take the first derivative, which is the slope of the tangent line to the graph of f. First thing I'm going to do is rewrite it. Now it looks like the power rule. Now I'm going to go find the first derivative. I'm going to bring that power down, times it by x, take that power, decrease it by 1. I'm going to clean that up. And no, you may not leave it like this. I do not want to see that negative exponent. Negative 2 is okay, not a negative exponent. Now, that is what I want to see. The first derivative is equal to negative 2 over x to the 3rd power. Next, my constant multiple rule. In other words, if y equals a number times a function, then what? So let's see. Take the derivative of this side, constant times my function with respect to x, equals, you just leave that constant alone. Don't do anything to it. Just leave it there. Then just go and take the derivative of this, whatever you've known from above. Let me show you what I mean. I have a couple of examples here. Let's see, cover that up. Y equals 3x to the 5th power. Well, that looks like this. That 3 times an x to the 5th is that function with respect to x. So it tells you when I take the first derivative, leave the 3 alone. Just take the derivative of the function. So I'm going to bring down my 5 times and then x and decrease that power. So it's still multiplication. So the first derivative is 15x to the 4th power. Here's another one. Y equals 5 over 2x to the 3rd power. And I want you to find the first derivative. Well, the first thing I'm going to do is I'm going to rewrite it. Now it looks like my constant 5/2 times my function. Now go and take the first derivative of the entire thing. In doing so, you just write down the constant. It just stays there. You don't do anything to it. Then you take the derivative of the rest of the function. Okay, bring down the -3 times x, decrease it by 1. That's -15/2 x to the -4th, which means the first derivative is -15/2 times x to the 4th power. This is what I want to see. You must tell me what's going on over here when you're still with the original function and when you are doing the first derivative. Then you must simplify all the way. Must. No choice. Next rule. Sum and difference rule. If you have two functions being added or two functions being subtracted, then this is how you take their derivative. You take the derivative of each piece of this function plus then the derivative of this one, or the derivative of the first one, then subtract, and then take the derivative of the second. So in other words, here is an example. Y equals x to the third minus 4x plus 5. This is actually, could be a function, this could be a function, and this could be a function. I have three pieces. How do I take this derivative? I take the derivative of each individual piece. So let's do that. The first derivative, well, of this piece, I'm going to use the power rule. Bring down the 3 and decrease the power by 1. I'm going to use the constant multiple rule. I'm going to leave the -4 alone. Now remember, this is to the first power. Bring down that 1 and decrease this by 1. It's just -4. And then the derivative of a constant is 0. That's the very first rule, constant rule. The derivative of a constant number is 0. That's why there's nothing else here. Done. It's completely simplified. Let us try another example. Yes, I'm going fast. I want to make sure you have plenty of examples. You really want to understand all of these. It's not that it's difficult, but it's a lot of algebra. This one here, let's say this is the function that you are given, and you're asked to take the first derivative. So again, I have 1, 2, 3, 4 individual functions. I'm going to take the derivative of each one of these. I like how this is written, this is written, this is written. This one here, I want to rewrite. I want to rewrite the whole thing. I want to see the constant out front times, and I want to see that function. Okay, and you can tell I said still y. Now here it comes. I'm going to take the first derivative. See, I told you I am. So the derivative of this piece, I just leave the -1/2, bring down the 4, x to the third. Leave the 3, bring down that 3, decrease that by 1. Leave that -2, take that 1, bring it down, x to the 0, well, that's just 1. And the derivative of a constant is 0. I am done, except I need to go and I need to clean that up. So -1/2 times 4 is -2, x cubed, plus 9, x squared, minus 2. One more example for sum and difference. What if I give you something like this? The original function says 2x to the third power over 3x plus 1 all over x. Well, I don't know how to do anything with that yet. So I need to make it look like something that I have been given. Well, why not go back and break it up into 3? I know this is one fraction. Why not break it back up into 3? Give each one of these numerators its own denominator. Then I'm going to look at, I'm still y. I'm still with my function. I'm still rewriting it. I'm going to clean that up just a little bit. I don't mind taking the derivative of that. I know how. That I know how. And that I know how. So now I'm going to take that first derivative. Leave the 2, bring down the 2. That goes to the first power. The derivative of a constant is 0. Bring down my -1 times x, decrease that by 1. That's now -2. Now let's simplify, clean it up. That's 4x. That's nothing. That's a -1 over x squared. I'm done. That looks good. let's do two trig functions. Let's find out the derivatives of sine and cosine. If I have these functions, this is their derivative. The derivative of sine of x with respect to x is cosine x. The derivative of cosine x with respect to x is negative sine x. These you will need to memorize. So let's use that idea. So let's see here. There we go. The first one, if I give you y equals 2 times sine of x, well, that's 2 times a function. I leave the 2 there, and I just take the derivative of sine of x. That's cosine x. And again, I told you I took the first derivative. This one here, I have a function, x plus cosine x. So that's the sum and difference rule. So my first derivative, I'm going to take the derivative of this first function, 1. The derivative of plus cosine x would be a negative sine x. And you're done. Let's do another one with trig. Y equals sine x over 2. And I ask you to take the first derivative. First thing I'm going to do is rewrite it. So I can see my constant out front times my function. That I can know how to take the derivative of. That I do not. That's going to follow underneath the constant multiple rule. So I leave the 1/2 alone. I take the derivative of sine of x, which is just cosine x. Done. All right. Now we're going to expand today's lesson. We're going to find the slope of a function at a point. So for an example, I have this function f of t equals 3 minus 3 over 5t. And we want to find the slope of this function, whatever it looks like, at the point 3/5 2. So we know how to do this with the limit definition. Let's learn how to do this with using the rules of differentiation. Well, first thing I'm going to do is I'm going to rewrite this. So 3/5 is my constant times t to the -1. Now, I'm going to go ahead and take that first derivative. The first derivative of f of t, well, the derivative of 3, the constant is 0. Leave the -3/5, bring down, as I multiply, -1 decreases by 1, that's -2. Now let's clean that up. Again, I still state this is the first derivative, so that's gone. Negative is positive. This is going to go in the denominator. There, I'm done. But I wanted to find out, there's my generic slope anywhere on this function. My generic slope of the tangent line to any point on this function. But I want to do it at this very specific point. So let's put in that x value, or t value, 3/5. Okay, don't let this overwhelm you. I'm going to cover this up so you don't overwhelm yourself. So I'm going to substitute in 3/5 for t. Make sure you put parentheses and it's squared. So let's look at the algebra. 3/5 squared means 3/5 times 3/5. Well, I can make that cancel out the 5s. So I have 9/5 left in the denominator. I'm going to multiply by the reciprocal. So that's 3 over 1 multiplied by 5 over 9. Simplify, 5/3. And so what is 5/3? The slope of the tangent line at 3/5 2 on the function f of t. The slope of the tangent line to the graph of f at 3/5 2. Let's do a trig one. I have some function g of t equals 2 plus 3 cosine t. So this is some function. Who knows? Well, actually we do know. We know what cosine function looks like. Then it's been vertically stretched by 3, and then it's been vertically translated up 2 units. Well, this point lives on this function, and I want to find the slope of the tangent line to this graph at this point. But not with the limit definition. I want to use the rules of differentiation. So this is already written well. I'm going to take the first derivative. The derivative of a constant is 0. This one here is the multiple constant, so I'm going to write down the constant, take the derivative of cosine of t, that's negative sine of t, multiplied together, so careful. So I'm going to rewrite that. My first derivative is negative 3 sine of t. Now it says at the point pi of negative 1. So why did I draw that? Because I was getting myself ready here. I'm going to evaluate it or find the specific slope at pi negative 1. So I put in pi, or t. Well, pi, this is cosine, and this is sine. Well, this is sine, that is 0. Negative 3 times 0 is 0. So the slope of the tangent line at pi negative 1 is 0. Sorry, yes, there is still more notes. It's not that it's hard, there's just a lot today. Now I want to, please notice, find an equation of the tangent line. Not just the slope of the tangent line to the graph of f, but I want to find the entire equation of the tangent line to the graph of f at a particular point. It must be at a particular point in order to find the equation of the tangent line. We have to know the slope. Well, here's an example. We're going to take the basic parabola, y equals x squared. We know that this point lives on there, right? Put in negative 2, you give out a 4. So at this point, on this original function, I want to find the equation of the tangent line. So first thing I do is I get the slope. I found the first derivative, which is this. This is the generic function for the slope of the tangent line anywhere on this graph. But I want to do it at a particular point at negative 2, 4. So let's put in negative 2 for x. So negative 4 is the slope of the tangent line at negative 2, 4. Great, we have the slope. But I want the entire equation. We're going to do point slope form. Y minus y1 equals the slope times the quantity x minus x1. So all I need for point slope form is the slope of that tangent line and one point that lives on that tangent line. I have both, the slope and one point. This point lives on the original function and it lives on the tangent line. The tangent line. So let's put both of those products in. The 4, the negative 2, the slope. There is the equation of the tangent line to the graph of y at negative 2, 4. That's the whole equation of the tangent line to the graph of y at negative 2, 4. Let's do it again. I have some function, I don't know, whatever it looks like. This point lives on there. But I want to find the equation of the tangent line to this graph at this point. All right, well, we better go and find the slope first, which is the first derivative of the tangent line. So bring another 3. That's 1. That's cleaned up enough. Now let's go evaluate it at negative 1. So there's the slope. The slope of the tangent line to the graph of y at, at this point, yes. But I don't want to find just the slope of the tangent line to the graph of the graph of y at this point. I want to find the entire equation. So I also need a point. What point? This point. So I'll use point slope form to write this equation. So let's see. So the negative 2 went in here, makes it positive. The negative 1 went in here, went positive. My slope is positive. So I'm going to distribute and then subtract 2. So it looks like it's in y equals mx plus b form. The equation of the tangent line to the graph of y at negative 1, negative 2. last page of notes. Determine the points, if any, at which the graph of a function has a horizontal tangent line. So here's a picture. Here's the f function. And I'm asking, is there any points like at here and here which the graph of the function has a horizontal tangent line which the slope is 0? So the only time my tangent line to my graph, like again when my pen rolls around and it's going to be tangent, is at a relative min or a relative max. Well, no, not always, we discovered, but most of the time. Not always. Remember, if I have a graph that looks something like this, that it could possibly have a horizontal tangent, and it didn't mean that it was a relative min or a max. So let's do that here. My function. And what am I asking? At what points does this graph, when I take its first derivative, is it going to be equal to 0? So let's go get the first derivative, and let's just go set it equal to 0. Because I took the first derivative. What is this first derivative again? The slope of the tangent line anywhere on the graph of f. Well, I'm asking what point is the slope going to be 0? Set it equal to 0. The slope of the tangent line be 0. Find out what x is. Just go and solve. So subtract 1. Imaginary. No real solution. Nowhere is there a horizontal tangent line. Nowhere. There isn't. There's either no relative min or max, or there's no place when I take my pin, does it become horizontal? Does the slope become 0? Nowhere. Nowhere. That's what this tells me, algebraically, without graphing it. Because right here, this should make logical sense. Let's try it again. Function. Y equals x squared plus 1. That's my original one. Let's go take the derivative. Okay, I did. What is that? The slope of the tangent line anywhere on the graph of this. Well, I wonder where the slope might be 0. So let's go ahead and let's set it equal to 0. And let's divide by 2. So x equals 0. Oh, that's what x value. At 0. So I put 0 in for here, except how do I know what y value? I go back to my original function here. Go back up here. I input 0 for x, that would be 1. Because I want to know what point on my original function will the slope of the tangent line be 0. So this is the point on the original function that has a horizontal tangent line, and a horizontal tangent line means my slope equals 0. Thank you. Now we're done.